Hi, everybody. This is topic 1 for our new unit on similarity. And we're talking about doing constructions of what a similar figure would be through a dilation. So the first thing that you should know is that a dilation is a similarity transformation. So we talked about rigid motions in Unit 2, reflections and translations and rotations, and those are the 3 other types of transformations, but all of those are rigid motions because they make the object congruent to what it was before. Congruent means they have the same size or the distance, and they have the same shape or angle measure. Now, a dilation is a similarity transformation, so it means it maintains the size. It maintains the shape. It keeps all the angle measures the same, but it does not always stay the same size under a dilation. And in this lesson, we're going to construct dilations of points and segments and lines, and do that through GeoGebra. So if you would, once you have this document open and saved in your drive in a Unit 4 folder, then let's get started. Scroll down to the part that says dilating points and click on this link right here. It should pop up this window right here. And what I'm going to do is I'm going to resize this a little bit, or just kind of move it so it's centered on my screen. And I'm going to construct a dilation of point B centered at A with a scale factor of 2. So what I want to do here is I want to get more tools. I'm going to scroll down to where I can get my pen tool. And it says I'm going to do a dilation of point B. That means that point B is my pre-image before the transformation happens. Centered at point A, that's the center of the dilation, and the scale factor is 2. Now, what you need to know is that when you do a dilation, points do not get bigger and smaller. Points always stay the same size. It's their location that changes. Now, the construction is very easy. If you find in the transform menu, there's an option that says dilate from point. And when you click on this, it says right here, first select object, then select the center point, then the scale factor. Well, what is it that we're going to be dilating? We're dilating point B. So I click on point B first. That's the object that I'm going to dilate. Then I'm going to click on point A next. That's the center of the dilation. The scale factor is 2. And there I get the point B prime is created. Okay, now if I click on my move tool, see what happens is I can move point A, and if I move point A closer to and further from point B, then point B prime moves as well. If I move point B, I can get point B prime closer to A and further from A, but it never, ever, ever is going to get closer to the point A than the point B is. And also, it always kind of follows B in a way that is on a line. So check this out. When a dilation happens, a dilation, the center of the dilation is like the sun shining. It's like a light bulb. And that's projecting rays away from it. So I'm going to click on the ray tool. And I'm going to start a ray at the point A, where the center of the dilation is. And if I put my ray through the point B, then point B prime will always fall on the same ray. Now, I like to have the rays be like a dotted line, so I'm going to change this to be a dashed line like this. And notice I cannot change the location of B prime. It can only be exactly right here because it has to fall on this linear path on that ray, and it has to be an exact distance from the point A and the point B. Now I can change where the point B is, and I can change where the point A is, but B prime is unmovable without moving the other two things, okay? Now, let's examine this relationship a little bit more, and I'm going to do some measuring. So if you scroll down to find the measure tool or the measure section, and you can measure distances. And with that, I'm going to measure the distance from the point A to the point B. It says that length is 2.2. Now I can measure the distance from B to B prime, and guess what? It's also 2.2. Or I can measure the distance from the point A to the point B prime, and it's double that, 4.4. Let me get these things arranged here a little nicer. So there's the distance. And we know that when this happens, the distance from A to B prime should be exactly double the distance from A to B. And the reason for that is because of the scale factor. Now, did the point B prime actually get any bigger? No. The point B prime is still just a point. It did not get bigger. It just moved farther from the center of the dilation. It moved double the distance from that center. It didn't get bigger. It just moved on that path. Okay. So once you have this picture, then grab a screenshot of this and upload it into the document that we started with the notes. I'm going to pause and I'll pick it up right after that. Okay, so here's my screenshot added to my document. And now what you can do is try these next two examples of dilating points and complete the think questions that are right here. When you're done with that, let's go down here to the dilating segments and then go ahead and click on this link right here. Okay, so now we're going to construct a dilation of the segment BC. Okay, so again, keep in mind that when you do a dilation, dilations are not going to make this segment, make the points themselves get any bigger or smaller. It's simply going to change the location of the points, and a consequence of that dilation is the segment will then also be changed. So we're doing a dilation of segment BC. That means that BC is the pre-image this time. And we're centered at point A, and the scale factor is 3/2. So let's go ahead and start by doing the dilation. So I'm going to go to the transform menu, select dilate from point. I'm going to select the object. Now notice where I'm clicking. I'm clicking between the points B and C so that the segment itself becomes highlighted. And then I'm going to click on the point A, and then I'm going to put in the factor 3/2 and hit enter. And there is my image. So here's the image BC. Now again, I can grab the point A and I can change where that falls. I can grab the line segment BC and I can move that around as well. But I can't move this segment up, down, left, right at all because both the points B prime and C prime can only be in that location that is both on the path. Now again, I like to show where the rays are for my dilation. That goes from the center point A through B, and B prime is on that as well, and A through C to C prime. And again, I like to make this just a dash segment like that. Okay, and so with that, I can also measure a couple of things here. So the dilation itself only moved the points. A to B has a distance of 3.8. Let me just move that a little bit so that it looks, let me move it, make it a 4. Okay, now if I measure now next the distance from A to B prime, that should be 6, because 6 is 3 halves, or as 4 times 3/2, it gives you 6. Now at the same time, if I measure the distance of this segment right here, or the distance from B to C, you get 3.6, and from B prime to C prime is 5.4. Well, let me change that so you can put it into some numbers that make a little bit more sense. How about if I make them a length of 2 and 3? See, now this length is exactly 3/2 times what that length is. The ratio of the image to the pre-image is equal to the scale factor. 6/4 is equal to 3/2 is equal to the scale factor of 3/2. So there's an example of what happens when we dilate a segment. The segment itself, as a consequence, did get bigger because of the scale factor, but it was only because these points moved on this path. The point B never got bigger. The point C never got bigger. Okay, so again, take a screenshot of that and upload it, and I'll meet you on the other side. Okay, so here's my image inputted here. I resized it so it wasn't super huge. And now you're ready to do question 5, a different example of dilating a segment. Okay, and then answer the think question, and then let's come down here and meet me and this link right here for the dilating shapes. So what you see on this and this link is you have all 4 questions within the one GeoGebra page. And you see that the difference is all of them are involving constructing a dilation of a triangle. But what happens is we're changing the center of the dilation, the center point O. In this case, it's the center point E, which is a vertice of the triangle. Then we have the center point N, which is a point inside the triangle. And finally, the center point M, which is when the point's on the triangle. So each one will be done the same way. So let me just do question 6 with you, and you'll see how this works. So I'm going to start again by grabbing my pen tool and just recognizing exactly what I'm doing in this question. So I'm going to do a dilation of the triangle JKL, which means this is my pre-image. It's centered at the point O, and the scale factor is 2. So to do my dilation, I'm going to dilate from the point because I'm dilating from a center point of dilation. This time, make sure you click inside the triangle, anywhere in here, not one of the vertices, not one of the sides, but just somewhere in the triangle, and all 3 sides of the triangle is highlighted at the same time. Then I'm going to click the center of the dilation, point O, and the scale factor is 2, and hit enter. There it goes. Now, again, the triangle itself got bigger. The size of the triangle is bigger, but it's not because of the dilation. The points, each individual point is the same size. The point K prime is not any bigger than the point K. L prime is not any bigger than L. It was because the distance of the points moved farther away from the center point O. So let's take a look at that with the rays here. With my lines tool ray, and I go from the line or the ray that goes from O through K also goes through K prime, and that through L and L prime, and that through J and J prime. All of those rays end up through both the pre-image point and the image point. So each point just moved further down that linear path. It did not get bigger or smaller. It just moved farther away. And when the whole triangle, or when all the points move farther away, then they move farther away from each other as well. And that's how we end up with a triangle that's bigger than the original triangle. Okay, we can also put in some measurements here and see that the length from O to K is exactly half the length from O to K prime, or that the length from K to L is exactly half of the length from K prime to L prime. But again, let's grab a screenshot. Now, zooming out makes it hard to see everything at once. So I'm going to make 4 individual screenshots, one for each question 6, 7, 8, and 9. So go ahead and do that, and then we'll see what that looks like inside the document. So again, I resized it so it wasn't super huge, and I'll just put 4 little screenshots in for each question 6, 7, 8, and 9, and then answer the questions that follow. So let's do the next section. When you're done with that, let's move on to here, finding the center of dilation. Click on that link, and then I'll meet you in GeoGebra. Okay, so first of all, let me just rescale this a little bit, zoom out so I can see what I'm looking at. Okay, now we're working backwards. You're told that the triangle PRO is the pre-image of triangle JEC. So let me start by grabbing my tool.